Duct leakage. So moving forward, we're actually going to be covering the specific Hurst procedures dictated by Title 24. So the actual reference for this procedure is going to be found in the reference appendices in RA 3.1. That's the link that you'll be able to find the document in under the California Energy Commission website. The document is also available for you to download from the LMS system. So diagnostic duct leakage is used by installer and raters to verify the total leakage that the total leakage meets the criteria for any sealed duct system specified in the compliance documents. So it's the overall leakage of the system compared to how much air the system is actually supposed to supply. The overall training goal is to familiarize yourself with the duct leakage testing equipment, protocols, and forms. The point of this PowerPoint is to give you an overview and an eyes-on what the equipment is going to look like, the general procedures for the test, how to set up the equipment, and so forth. Once you're actually in your field training, then you will go through it in detail and actually setting up the equipment and yourself. It would be hard to learn this procedure without having the actual equipment, but at least by reviewing it step by step in the PowerPoint, you're then going to have something to reference back to once you actually get to your field training. These are the sections that we're going to cover in this PowerPoint. So we're going to go through the equipment specifications. So basically, there are specific equipment that you have to use for this test, and we're going to go through that in the following slides. So all pressure measurements shall be measured with an equipment having an accuracy equal to or better than plus or minus 1% of pressure reading, or plus or minus 0.2 pascals, whichever is greater. All pressure measurements within the duct system shall be made with static pressure probes, such as a Dwyer A303 or equivalent. Now, you guys are not going to have to worry about verifying this information once you actually get your equipment. The equipment that's used in the industry on a nationwide level, it's very unique. There was only 2 companies that offered this equipment. However, if new equipment ever were to come on the marketplace, it's important for you to know the measurement specifications so that you can pick accordingly. Airflow measurements shall be measured with equipment that has an accuracy equal to or better than plus or minus 3% of reading, or plus or minus 1 CFM, whichever is greater. So there's 4 different manometers in the industry that you'll see out in the field. The top 2 are made by the Energy Conservatory or Minneapolis. The bottom 2 are made by Retrotech. The DG700 is the main manometer used by the Energy Conservatory. The DG3 is the predecessor of the DG700. It's an older model, but nonetheless is still usable. The DM2 or DM2A is the older model of the Retrotech, and the DM32 is the newest Retrotech gauge, which uses a full touchscreen interface and digital reader.
All instrumentation used for duct leakage diagnostic measurements shall be calibrated according to the manufacturer's calibration procedure to conform to the accuracy requirement specified in RA 3.1.2. Now, each manufacturer has different specifications for calibration. Some of them require yearly, others are on a 5-year cycle. So you do need to go to the manufacturer and calibrate based on their recommendations.
The actual equipment for duct pressurization shall consist of a duct pressurization and flow measurement device meeting the specifications in section RA 3.1.2. And on the right hand side, you're going to be seeing pictures of the 2 duct blasters available on the market right now. The top one is the Minneapolis, the bottom one is the Retrotech. And obviously the associated manometers that go along with those systems. Please keep in mind that with the Retrotech duct blaster, you are allowed to use Minneapolis manometers, but not the other way around. If you're conducting a duct leakage to outside test, and we're going to talk about that later on in the procedures, additionally, you're going to need a blower door in addition to the duct blaster. In addition to the duct blaster, duct leakage to outside obviously should include a fan that is capable of maintaining the pressure within the conditioned space in the house at 25 pascals relative to the outdoors. So we're going to be talking about the blower door in much more detail in future presentations, but nonetheless, just keep in mind that if you're hearing duct leakage to outside, you'll need the blower door and a duct blaster to conduct it. And finally, a smoke machine. The smoke machine shall be able to introduce controllable, non-toxic smoke. The means for generating smoke shall have sufficient capacity to ensure that any accessible leaks will emit visibly identifiable smoke. So the point of a smoke machine is if you're investigating the location or source of leakage within a duct system, you will be able to basically blow smoke into the system while pressurizing the ducts so that you can visually identify where the smoke is coming out of, hence identifying the leakage points in that system. And now we're going to talk about shortly about duct leakage and delivered BTUs and how duct leakage affects the efficiency of HVAC systems. So why is duct leakage important? Duct leakage reduces delivered BTUs and reduces system efficiencies. This translates into a higher energy use and a higher cost to the homeowner. The formula below is what we use to calculate delivered BTUs. It's 1.08 times CFMs times delta T equals the BTUs delivered. So 1.08 in that formula is a multiplier and it's a constant. It will always be 1.08. The CFM is the delivered supply amount of air by the system. So this is the amount of air that's coming out of the supply side. The delta T is the difference, the dry bulb temperature difference between the supply and return temperatures. So like I mentioned in the building science portion of the training, the triangle means delta, which means difference. Delta T stands for difference in temperature, in this particular case, between the supply and the return temperatures. So in our first example, we're going to see an example of a system that has no leakage. We have 75 degrees interior temperature, and we have a system that operates 1000 CFMs. And because there is no leakage, you're going to have 1000 CFMs being pulled into the return and 1000 CFMs being supplied through the supply side. Now the delta T is 20 degrees. Please note that this temperature drop between supply and return is a default value for all systems. That is just an industry default. So the difference between supply and return is 20 degrees unless you know otherwise. But if we know that the interior temperature is 75, then with a 20 degree difference, the supply temperature will be 55. So if we plug in those numbers into our formula, you're going to have 1.08 times 1000, which is the amount of air being supplied, times 20, which is the delta T, which equals to 21,600 BTUs delivered. So our second example would be a supplied site leakage example, and let's see how that works out. So same house. We still have 75 degree interior temperature. It's still a 1000 CFM system. There's a delta T of 20 degrees. The only difference here is the fact that now on the supply side, instead of being 1000 being supplied into the house, you're losing 150 into the attic. So only 850 are supplied into the house, and you're losing 150 somewhere through supply ducts in the attic. Now if we plug in the same numbers into the house, into the formula for the house, it's going to be 1.08 times 850, which is the actual supply CFM into the house, times 20, same delta T, equals 18,360 delivered BTUs. In the third example, we have return site leakage. So the only difference with this scenario is the fact that now we don't know the temperature on the return supply side, because now we'll be sucking air from the attic. So we have 75 degree interior temperature and we have 135 degree attic temperature because it's a hot attic. So therefore the hot air being sucked into the return plenum, it's going to affect the temperature of the actual air being introduced in the system. So we have 850 CFMs coming in from inside the house through the return grill, and then we have 150 CFMs being introduced from the attic through some kind of return leak into the system. So like I said, we don't know the actual temperatures because they will be affected by the temperature of the air leaking into the system from the return. So we have to figure those out. So if a 1000 CFM system is leaking 150 CFM, that equates to 15% of leakage. In this example, the system is pulling 15% of its nominal capacity from the attic. This leaves only 85% coming from the living space of the house, which is the actual return grill. We have to calculate the system temperatures based on the percentage of leakage being introduced into the system from the unconditioned space. And the leakage percentage will vary in every system. We're just using these numbers as an example. So how do we figure that out? So if you look on the right hand side of the instructions, so we said the 15% is coming from return leakage, 150 of 1000, that's 15%. So the decimal equivalent of 15% is 0.15. 85% is coming from the return of the house, that's 0.85, which is the decimal equivalent of 85%. We know we have 135 degrees of attic temperature, and we know we have 75 degrees of return or house temperature. So we're going to figure out what the percentage of each one of those degree differences are. So 0.15, 15%, times 135 degrees equal 20.25 degrees. We then multiply 0.85, which is 85%, times 75, which is the air from the inside of the house. So 0.85 times 75 degrees equals 63.75 degrees. You then add the two temperatures together. This is the estimated temperature at the return plenum. So 20.25 plus 63.75 equals 84 degrees, and that's going to be our return temperature. As we mentioned earlier, knowing that the default temperature drop between return and supply is always 20 degrees, by having determined the return temperature, we can now estimate the supply temperature. So 84 minus 20 equals 64, and that's going to be our supply temperature, 64 degrees. So now that we have our supply temperature, we can figure out delta T. So 75 minus 64, the difference between return and supply, is 11 degrees. So now we plug in those numbers in the formula. 1.08 times 1,000, because there's still 1,000 CFMs being introduced into the house, times 11, which is the delta T, equals 11,880 delivered BTUs. As you guys can see, the number gets lower and lower. So in our fourth example, you have return and supply side leakage. Same house, we still have a 1,000 CFM system, we still have 75 degrees inside the house, and we still have 135 degree attic temperature. We're leaking 100 CFM return leakage and 200 CFM's supply leakage. So now, because we already have the delta T's in place, we're going to plug in those numbers into the formula. So you still have 1.08 times 800, because those are the supply CFMs. So you still have a 1,000 CFM system that's leaking 200 CFMs into the attic. That means you're only supplying 800 into the house. So you have 800 supply leakage times the delta T, which is staying the same because the temperatures haven't changed. So with a delta T of 11 degrees, the delivered BTUs in this particular scenario are 9,504 BTUs. So in conclusion, a leaky system would only deliver a percentage of its system capacity, maximizing energy cost and decreasing the life of the unit. Because the unit will most likely run longer than it needs to, it will decrease the amount of time or the life expectancy of the unit itself. And these are our examples summarized. So example 1 was a no leakage system. It was delivering 100% of its capacity. Ideally, that's what we want. And it was delivering 21,600 BTUs. In example 2, we had a supply leak, and that resulted in an 85% capacity delivery, only delivering 18,360 BTUs. In example 3, because of the return leak, it was only delivering a 55% capacity because it brought the BTUs down to 11,880, being much lower. So you're about half of the capacity of the unit. And then in example 4, where you had both supply and return leaks, it only delivered 9,504 BTUs, being approximately 44% capacity. So you guys can see where the problems lie when it comes to duct leakage. Now, where does duct leakage come from anyway? And these are just some of the most common examples that you'll see. So on the left-hand side, you'll see improperly sealed duct connections. So anywhere where there is a connection of a duct to another duct, or maybe a plenum or a junction box, there's the potential that it's not going to be connected properly and there's going to be leaks. So if improperly sealed duct connections, we'll see a good amount of leakage in the overall size of the system. In the middle picture, gaps between register boots and drywall should be sealed. In this particular picture, they're not. So if they don't stay sealed, whether it's a return grill or a supply grill and register, it doesn't matter. If it's a return register, then and those edges are not sealed, the return will then pull air from the subfloor or from within the building cavity rather than the house. If it's a supply register, then the supply register will push air into the building cavity rather than into the house. So the gaps between the register boots and the drywall have to be sealed. And then last, unsealed penetrations in the cooling coil. So any kind of penetration within the cooling coil casing has to be sealed somehow. If not, you're going to get supply air escaping from it. So it's important that those particular penetration points are sealed. Now there's plenty more areas where the system could be leaking from, but these are by far some of the most common. Once you actually get in your field training, you're going to be working with a live system working in an actual house, and you'll be able to identify many more areas where leakage could be coming from. Now we're going to be talking about determining nominal airflow for the system.
In order to determine the allowed duct leakage, you must first determine the system airflow. This can be done by one of three possible means. The first one is default air handler airflow, second is the nominal air handler airflow, and third, the measured system airflow. Airflow is always going to be measured in CFM. So the first option, and most likely the least used, is going to be the default air handler airflow. This is to be used only for homes where the duct system is being tested before the air conditioning and heating system is installed and the equipment specification is not known. If you know the size of the heating and cooling equipment, you cannot use this method, which is why it's not going to be used very often. If it is a heating only system, the default air handler airflow shall be 0.5 CFM per square foot of conditioned floor area.
The nominal air handler airflow is calculated in a couple of different ways. So you have the heating method, and the formula for that is 21.7 times the kBTUs per hour of rated heating output capacity, or the cooling method, which is 400 times the ton of the condensing unit. You can use whichever method gives you the greater airflow. Keep in mind though, a heating only system has to use the heating method obviously because they don't have a condenser to go by. So here's an example for the heating method. The furnace has 80,000 BTUs of output. So the kBTUs for 80,000 would be just 80. So 80,000 BTUs equals 80 kBTUs. So the formula is 21.7 times the kBTU of output capacity. So that's 21.7 times 80. So the nominal airflow for that particular unit is 1736, 1736 CFM. Keep in mind, airflow is always measured in CFM. The cooling method for the same scenario, that particular system has a condenser that's rated for 4 tons of cooling. So the formula is 400 times the tons of cooling capacity, 400 times 4, that gives us a nominal airflow of 1600 CFMs.
And the last method is the measured system airflow. So this one can be used anytime you can actually measure the airflow of the system with one of the devices that we'll talk about in a little bit later in the adequate airflow section. So the airflow will be measured with those same procedures that you'll be using for adequate airflow, and that's found in RA 3.3.4. The airflow will be the actual CFM measurement that's recorded when conducting that procedure. And again, we will be covering that later in detail, the different types of equipment that you can use, as well as how you will collect that data.